Okay, good afternoon. Welcome to this session on the vSphere distributed switch. We're going to talk about best practices. This is going to be about the vDS and NSX. So I have to warn you that we have a relatively packed session in terms of content. So I would appreciate if we could push the question to the end. Shahzad and I will be there for as long as you want. We can go outside even to carry on answering your questions after the session. So if you have, of course, an urgent question, please go for it. But we need to be going on relatively quickly if we want to pack all our content in 1 hour. Also, if you have attended this session last year, I have to warn you that you have something like 90% identical content. We basically remade the demos and made some enhancements, especially on the second part that Shahzad is going to present on operation, because there have been a lot of changes there. So let's go quickly over some disclaimer slides you've certainly already seen, and even that kind of marketing slide that is pretty much just telling you that NSX is doing well and is being adopted right now in the field. This is the outline of our presentation today. We're going to go over an introduction that will not only go over some familiar concepts on the vDS, but explain some few terms that will be necessary later in particular for the second part, where we're going to discuss the best practices on how to connect your virtual switch, your NSX host, to the physical network mainly. The third part is going to be focused on operation and troubleshooting, and Shahzad will take over for this before presenting a very short conclusion. So without wasting any additional time, let's start with a vDS architecture. It's a very high-level introduction. Okay. So first, what is NSX? I hope you already had some overview about NSX, but in just 2 words, a little bit more maybe. NSX is VMware's network virtualization solution. Our goal with NSX is to provide not only the basic switching and routing functionality, but even more advanced networking features like firewalling, load balancing, VPN in software, meaning that we're going to achieve those functions on your hosts, on your servers, on the hypervisor of those hosts. Shahzad and I are both network guys, so this is going to be really focused on the networking part. Even if we won't go really further, the first icon on the left, which is about switching, that's really the base we're going to talk about today. In this room, I can hardly see you, frankly, but who is more of a network admin? So not that many, I would say a third. Who is a server admin? I would say more than a half. Who is a storage admin? Probably another third. So that's, I would say, the expected distribution in a VMworld session, and I think hopefully the content is really appropriate for that. So it's not going to be too technical on the networking side, but it's about pretty much explaining how you're going to insert NSX in your environment. So just like all networking things, NSX can be presented in layers if you want. We're going to start not by the gray part, which is a physical network infrastructure. We're not going to talk about that today. The lower layer for us is on your host. I told you earlier on that we want to switch, do routing, firewalling, etc. on your host directly. This is a software data center, basically. So this part is going to be achieved by some components that run on each and every hypervisor in your network. Those are kernel modules that we push to your hypervisor, and we're capable of doing the distributed functionality like switching, routing, and firewall directly in the kernel of your hypervisor. We also have an edge, which is basically a virtual machine that is capable of providing higher level functionality. also firewalling, VPN, load balancing, etc. This is a VM form factor. This is our data plane, meaning that those are the components that are really forwarding packets in the system. Just above that, we have the controller or the controllers. This is actually a cluster of virtual machines that is responsible for programming those different components that are distributed across your data center. So they're the ones that are going to push MAC addresses, that are going to push VTEP IP addresses. We'll talk about that later on. They're responsible for setting up everything if you want. They're in a cluster for two reasons, redundancy and scale. So redundancy meaning that, of course, if one of them or even two of them fail, you still have a backup that is capable of operating the fabric. Actually, they're completely outside of the data plane, meaning that if really all of them failed at the same time, which is supposedly unlikely because there are several of them, you would still be able to switch traffic, actually. It's only setting up new stuff that would not be possible. So, yeah, redundancy and scale out, of course, the more you are, the more power you have. And the different functionality are, the responsibility for the different components in the system are going to be spread across this cluster. Above the controller, we have the manager. The manager is a single point of entry where you're going to program your network, your environment, your networking environment, so we can accept REST APIs, for example, and that's also where your cloud management platform, whether it is vRealize Automation, OpenStack, or whatever, is going to connect. So this is a part that is NSX. Above, it's not NSX anymore. Below, it's not NSX yet. The focus of this presentation, as I already mentioned, is really going to be on the switching part and more specifically on the vDS, so the vSphere distributed switch. The vDS is an upgrade, an enhancement over the VSS that you probably also know as a vSphere standard switch. The vSphere standard switch used to be managed on a per host basis, just like a physical box if you want. And what the vDS adds on the top of the VSS is a global view of the network. The vDS is capable of representing a virtual switch that spans the whole data center. And for example, here I've represented several virtual machines. Irrespective of where they're located, it looks like they're connected to one big virtual switch that spans the whole data center. That's basically the enhancement that the vDS provides, a way of managing your switching needs for the whole data center from a single place. Some few terms that, again, I'm sure you know that I'm going to go over very quickly. A DV port is a port where a virtual machine attached on this VDS. That's probably the most important concept here. We also have a DV uplink, which is new in the VDS, and that represents the connectivity of this virtual switch to the physical world. And both those components are grouped. So we have a DV port group that groups DV port that have the same characteristics. It allows us to configure several ports in one shot. And we have DV uplink groups that do the same for your uplinks. Nothing groundbreaking right now. So again, the beauty of the VDS is this centralized management. So what you used to do on a per host basis, now you can do it globally on your network. So for example, here I am managing two virtual machines that are attached to one blue DV port group A. This is something that you create. It looks like those two virtual machines are attached to, again, a single switch from the logical perspective. But from a practical standpoint, in the physical implementation, you see that our two VMs are on two different hosts, and this DV port group is actually configured on two different hosts too. So this is something you would have had to configure manually with the VSS. This is done automatically for you by the VDS. So that's the big added value of the VDS. If I had another virtual machine in a different DV port group, it will be instantiated on the host where it is needed. Another interesting aspect of the vDS is that because it automates the configuration of those local components, you don't waste resources on the hosts that don't require this DV port group B, for example, right? This is something you could have done manually with the VSS, and again, the vDS is doing it automatically for you. Another concept that I need to introduce very quickly is the concept of VM kernel interfaces, or vMechanics. So, of course, virtual machines need connectivity to the network, but they're not the only one on a host. You also have some local services that need to communicate through the network, and for this, we're equipped with this VM kernel interface, even if it's actually not represented in the diagram that would be on this. For example, this is a management module. It would have an interface that connects to a DV port in its dedicated DV port group here. So we have several of those services that leverage different vMechanics that are themselves attached to different DV ports, which then can be grouped in DV port groups. They can be several DV port group or one DV port group. This is something you configure. Now, I'm still talking about, there is still nothing NSX related in what I'm talking about yet. It's coming, please be patient. It's only 5 minutes. So, a VLAN back vDS is what we've always known before NSX. Basically, you have a one-to-one association between a DV port group and a VLAN. So if I create a new DV port group, and if this DV port group extends beyond a host, it needs to be back to be associated to a VLAN so that its network traffic can be extended to this other host. So this solution, which works fine, has two, I would say, drawbacks. The first one is that you have an association to the physical world. So here I have one DV port group, the DV port group A in blue. Suppose I want to create a new DV port group. So I've created my DV port group brown. This is something I can do on the whole data center from vCenter, right? This is the beauty again of the vDS. However, I need to make sure that I have a second VLAN, here VLAN 2, to associate to this new DV port group. And that's one of the problems here because, well, if this VLAN does not exist in the physical infrastructure, you need to now go to your network team and ask them to create this new VLAN. This is something that we know can take a lot of time. This is an administrative effort between different teams, and you can spend actually weeks on that, we've seen in the worst case. Another way of doing this, and this is why when I was working at Cisco before, I would get some customer who asked, oh, I want to have 4K VLANs on each and every port in my network. And frankly, in an enterprise environment, nobody needs 4K VLANs. The reason why people are asking for 4K VLAN is that they want to pre-provision every VLAN so that now when you go into the vDS and you ask for a new DV port group, there is already one VLAN available for this DV port group. This is, of course, not really scalable at the hardware level, and it's generally a problem. So this is a big issue in terms of coupling to the physical network. The other part is something that probably the network guys here are going to be more sensitive than the server guys, but typically we're trying to avoid spanning layer 2 on the whole data center. I'm not going to insist too much on that, but one of the issues of layer 2 is very flexible and still necessary by, needed by many applications, but the problem with layer 2 compared to layer 3 in a nutshell is that a local problem can impact the whole layer 2 domain, whereas problems are typically more localized with L3. If you have a routing problem issues, typically the problem is limited to where this routing table issue is located, whereas if you start having a loop somewhere in your network, this is going to spread all over your layer 2 domain. So as a general rule, when you're designing a network, you tend to have smaller, contain layer 2 domains so that you don't put all your eggs in the same basket, I would say. If you put all your network in a layer 2 domain, it could be killed by a single issue that introduces a loop. There are some other factors to consider here. That's not the purpose of this presentation, but let's say that it's a goal to limit the span of your layer 2 domain in a network. So how are we going to solve the issues with NSX? We're going to use an overlay. And this overlay is based on an encapsulation. So basically, we're going to tunnel our traffic using tunnels between your hypervisors. This is going to be described at length in the next slides, so don't get too confused yet. The encapsulation that we're going to use is VXLAN. And for us, VMware, VXLAN is just one choice among many. We don't really care about the encapsulation we use. This is something that typically network vendors are very concerned about because their ASIC can only do so much, right? For us, this is just one encapsulation we chose because it was widespread and it's a kind of de facto standard in the industry. But we could easily switch, and actually we have plans to use, for example, a new encapsulation called Geneve in the near future. But this is, again, not really important. What you need to know about tunnels and overlay is that we're taking a layer 2 frame in one side, we're inserting it into a tunnel, and the VTEP that is represented on each side of this tunnel is a virtual tunnel endpoint. So this is where the frame enters the tunnel. It is being encapsulated in IP, goes through the tunnel, and is decapsulated by the other VTEP at the end of the tunnel. That's all that is really important. Why IP? Because IP is a predominant networking technology. Every vendor runs IP. And this is L3 based. So this little fabric issue, L2, the span of the layer 2 network we were concerned about, right, is a non-existing problem if you're only routing traffic. So by encapsulating your layer 2 frames over an IP encapsulation, you don't require any layer 2 connectivity at all in your network. So that's a big added value that we're provided. And the second added value, we'll see that in the next slide, is that we're also decoupling from the hardware in terms of creating those layer 2 domains, those VLANs. So the reason why I introduced this VM mechanic earlier on is that VXLAN on a host running NSX is just an additional service that we have implemented on your hypervisor. So when a virtual machine sends some traffic on its logical switch, on this local virtual switch, I would say, this traffic is going to be encapsulated through this VXLAN VTEP service that we have added to the network, to the host, sorry. And we see that this VXLAN VTEP is connected to its own DV port group that I've represented in orange on this slide. There can be several VTEPs, but they will share the same DV port group. And this is important. We'll see about a little bit later why. Something I need to point also here is that what used to be called a a DV port group is now called a logical switch. When it's backed by a VXLAN, it's called a logical switch. So for me as a network guy, VLAN, logical switch, DV port group, broadcast domain, L2 domain, they're all the same, right? We're just talking about a layer 2 domain, a broadcast domain. So this is a new name that you will be seeing if you're using VXLAN. So now let's show an example of what happens now when two virtual machines on different hosts communicate through VXLAN, through this tunnel. So the example is assuming that VM1 sends a frame to VM2. So first this frame is going into the local virtual switch of the host, and it is forwarded to the VTEP that is local to this host that encapsulates it into IP. So the VTEP locally knows that the MAC address of VM2 is associated to an IP address on host B. You have this table. You have a lookup in a table that has been pre-populated by our controller. And basically now it's just a matter of sending this IP packet across your IP network to host B. So this is just plain routing at that stage. On host B, I recognize that it is a packet that is going to the IP address of my VTEP. I decapsulate the packet and recover this L2 frame that I can now switch locally to my logical switch A to VM2. So pretty straightforward. It's basically the same path as before, except that we have this additional step of going through a VTEP. But the beauty now of this model is that if I want to create my new layer 2 domain, my logical switch B now, nothing changes from the network point of view. For example, here I have my brown logical switch. I need to send a frame from VM4 to VM3 on this logical switch. It's going to go through the VTEP, being encapsulated, transmitted as an IP packet across the network, received by the other side's VTEP, decapsulated, and eventually forwarded to the remote virtual machine. So you see, I've instantiated a new layer 2 domain, what used to be a DV port group, now called a logical switch again, but I didn't have to change anything on my physical infrastructure. So this is also the solution to this other problem of coupling physical to virtual. Now I have my virtual network that is entirely independent from my physical network. I configure my physical network once. I don't mean that it's all plug and play and that you don't have to touch your physical infrastructure at all. But once I've configured my VTEP correctly, that they can route between each other, then there is nothing else you need to do on your physical infrastructure. So to show you how easy it is to create layer 2 domain and use them, we have a short demo for that. And during this demo, it's very short indeed. So I'm going to tell you a little bit ahead of time what we're going to do. We have 2 hosts, and each host has already pre-configured, has been pre-configured with a virtual machine. That's 2 hypervisors, of course. And each of them has a virtual machine already pre-created. Those virtual machines have a VNIC, a virtual interface, that have been configured with an IP address in the same IP subnet, let's say subnet 10. We're entirely decoupled from the hardware, so we don't care about the IP address we put. Why not 10? And we're going to create this logical switch, this virtual broadcast domain, and attach our 2 virtual machines to this broadcast domain. And of course, once we've done that, we're going to check that we have L2 connectivity by just doing a ping within the same network. So pretty straightforward, and you'll see this is a matter of the demo is like 1 minute. So this is very fast and it's real time. So what I'm showing you here is first, of course, that my virtual machine cannot reach each other. They're pinging to each other and it's failing. Next step, I'm going to the NSX tab and the logical switch section. I'm going to create a new logical switch. And you'll see how fast it is. It's basically a matter of giving a name to this logical switch. There is also the need to populate a transport zone. I'm not going to elaborate on that, but a transport zone pretty much represents the span of this logical switch on the physical infrastructure. You don't necessarily want this to extend too much, so you can decide which hosts are part of this transport zone. So they cannot ping yet, but I'm going to select those 2 virtual machines, and you'll see that their virtual interface is right now disconnected. And I'm going to assign them to this logical switch. So now they're assigned to the same logical switch. And now, of course, they can ping. So this demo is real time. I didn't cut anything. I didn't edit anything. This is really how fast it is to create a layer 2 network from scratch and instantiate it on your data center without changing anything on your physical infrastructure. So no need to negotiate VLANs with a network team or to pre-provision zillions of VLANs so that you always have one available. So now let's look at the configuration of this vDS, how we're going to configure our hosts to run NSX, basically. So first, very basic recommendation in terms of redundancy. Typically, in networking, you don't want to rely on a single box. You want to have always physical redundancy. So typically, your hosts are connected to two top-of-rack switches. Be careful that, again, in this list that I'm going to go through quickly, this is only a recommendation, it's not a rule. I mean, some customers have a rack as a unit of failure. The whole rack can fail. I mean, they connect all their hosts to a single top-of-rack switch. If the switch dies, they have another rack that takes over, for example. That's one model that is valid, of course, but many customers are typically dual homing their host to two different top-of-rack switches. We support up to 32 uplinks, but the trend now is to go to 10 gig interfaces, and typically you only have two uplinks in that case. And in that specific case, we recommend that, of course, you assign those two uplinks to the same vDS. This is something that was not typically done with the VSS, and well, at least with the VDS without. When we had, let's say, 5 or even 7 uplinks on a box. You used to have 1 gig interfaces. One would be dedicated to management, one for storage, and etc. And you had only a limited number of interfaces, uplinks for your data traffic. When you only have 2 uplinks, you don't want to dedicate one uplink just for management traffic. I mean, you don't need 10 gig for your management traffic. So now we recommend that you're basically allowing all your different VM mechanics on both interfaces. And we have some more advanced mechanisms that allow you to reserve bandwidth, for example, for a particular category of traffic. vSphere 6 introduced NIOC v3, which is much more elaborate in this respect. It allows you to create reservation limits and share for any category of traffic. It allows you to restrict bandwidth and assign QoS parameter on a per VM basis also. We recommend that you're using, that you're leveraging hardware capability for your NICs. If you have some NICs that support natively VXLAN, will have better performance, obviously. And I have some few spanning tree related configuration recommendation. I'm going to go very quickly through this. Basically, a host will never switch back at layer 2 traffic that it has received on one uplink in another, on one of its other uplinks. So you don't have to run spanning tree, in fact, through your NSX domain, and you can configure your physical port as what Cisco called port fast. The official term is an edge port from the spanning tree perspective. This allows you to converge faster. You skip some few initial stages in the spanning tree. We have on many switches the capability of tracking BPDUs that you would receive on the physical switch with a feature called in Cisco BPU guard. You don't need that technically, because now your traffic is going to be encapsulated over VXLAN. So even if a virtual machine was inserting some BPDUs, your physical switch wouldn't see it anyway. But it doesn't cost you much to still configure these parameters on your physical port. That's kind of safety mechanism. Thanks to VXLAN, you can get rid of your end-to-end layer 2. So again, to be capable of creating a DV port group, you used to have the requirement of extending L2 in your data center. This is not necessary anymore, thanks to VXLAN. And actually, even vMotion now doesn't have any requirement on layer 3. This is on layer 2, sorry. We have the capability of seamlessly and very simply doing vMotion over an entirely IP routing-based networking fabric. This is something that has been introduced in vSphere 6 also. So let's go over the different ways you can connect your uplinks with NSX. I'll start first with some general concepts on the vDS without NSX. Typically, again, your host is attached to several uplinks, through several uplinks to several top-of-rack switches for two reasons. Redundancy, obviously. If one link fails, you want to be able to fail over to the remaining uplinks. And also added bandwidth. And I have to warn you here that it's not because you have 2 times 10 gigs on your uplinks that you really have 20 gigs worth of bandwidth in your network. This is very important. Best case, you have 20 gigs, but worst case, it could be as bad as just 10 gig. So this is an important concept. The only thing that we do when we are sending traffic over 2 uplinks is that we distribute this traffic over this uplink. And depending on the distribution, you can go from 10 gig or 20 gigs. Before I go further on this part, something that is very important in networking is that we always send a particle flow on in only one direction. Even if we have several paths toward a destination, and I'm talking here about not only routing, not only bridging, but also routing, we always try to pin a flow to a particular path. And this is because you want to avoid out-of-order delivery. So if you were sending the same flow over 2 paths, one path could be slower or more congested than the other, and you could end up with out-of-order delivery to your destination, which sometimes confuses or at least reduces the performance of the IP stack on the remote side. So we're always trying to pin a traffic to one path. So when we're talking about pinning traffic on a VDS, on a host running this VDS, we have 3 main ways of doing it with a VDS. We can do this at different granularity level. One granularity level is at the level of a DV port group. What it means is that for all the packets sent by VMs belonging to one particular DV port group, we're going to send all the traffic from this DV port group to one particular uplink. We're pinning a DV port group to one uplink. For example, here, DV port group A is pinned to the left, DV port group B is pinned to the right. That's very coarse granularity. Now we can be a little bit more granular. We have an option called source port hash. And now we're going to pin the VM NIC of a virtual machine to a particular DV port group. So to a particular uplink, sorry. So within the same DV port group, now, based on your virtual machine, I will send on either the left uplink or the right uplink. More granular. And most granular is per flow. So within the same DV port group, for the same virtual machine, I can now pin my traffic on a per flow basis to either the left uplink and the right uplink. So here we have a little catch. When we're doing that, because we're sending traffic with the same MAC address, right, the virtual machine has a MAC address, and because we're sending traffic from the same MAC address, in order to not confuse the physical infrastructure, we have to send it on a single interface in theory. So those 2 physical uplinks have to be bundled in a port channel so that there is only one MAC address table on the physical infrastructure. Otherwise, it will look like a MAC move. So those are the 3 different models, from the simplest and coarsest, if you want, to the most granular and most efficient. Why is it important to be granular, by the way, is that it's a matter of distribution. If you have a big item that you need to well, let's say I'm splitting oranges into baskets, right? There is only so many oranges that can go in either baskets. It might not be if you have 3 oranges, for example, well, you will have best case, you will have 2 oranges in one basket and 1 orange in the other basket, and that's not ideal distribution, right? Now, if you're sorting, I don't know, sand, very, very small items, then you can expect that you will have a much more even distribution between your 2 baskets because it's much smaller. So even if you do this at random, the pinning is almost random, right? You're much more likely to have an even distribution. So now let's see how those three models, by the way, there is one model that you probably know that is not there. It's load-based teaming. This model is not supported as NSX, and we'll discuss this in the corridor later, why we don't have time to go over that. So I'm going to show you how those three models map to NSX. And the first one was this per port group model. So I'm pinning a port group to an uplink. So this is still possible with NSX. The problem is now my traffic is always going to go through a VTEP, which itself is mapped to a single DV port group. Even if I had several VTEPs, they would still be leveraging the same DV port group. So now, if you're pinning your traffic to an uplink based on the DV port group, well, you're always going to use the same uplink. So in this model, the explicit failover is really active standby, at least for the VM traffic. You can still do some other form of active standby per DV port group for your other infrastructure traffic, your management, vMotion, etc., right? But the VM traffic is going to go through a single uplink with this model. So not the best in case of load distribution. Not bad if you want to guarantee a minimum bandwidth, make sure that your bandwidth allocation for your VM is consistent. If you have a link failure, well, you were limited to 10 gig. If a link fails, you still have 10 gig. The other model is source-based, where we want to pin on a per virtual machine VNIC basis. So in order to achieve this model, we're going to require two tunnels. We'll have, in that case, NSX will create automatically for you two different VTEPs. And the hash in terms of source port will basically assign a virtual machine to either, here in that case, VTEP 0 or VTEP 1. And VTEP 0 will go on the left uplink, VTEP 1 will go on the right uplink, for example. So very simple. In case of failure, we're going to switch basically the VTEP itself. Let's say that the left uplink fails. VTEP 0 will move to the right uplink, and thus we converge all the affected virtual machines. And the last model, our port channel based mechanism, is relatively simple. We only need one VTEP in that case, and this VTEP represents the port channel on the physical infrastructure. So which model do you want to choose? So there is a reason why we have those three models, that they all make sense. And I don't want to say, oh, use this one, it's the best. This one actually is the best in terms of convergence time and probably bandwidth utilization. In theory, it's the best. The reason I don't necessarily recommend this is that it requires to have a port channel on the physical side. The port channel technology itself is relatively standard and well-defined, but because we want to have this port channel ending on two different boxes, what we actually need here is a distributed port channel, something that Cisco calls a VPC or VSS, that Arista calls MLAG, split MLT if you have some old memories. But this distributed port channel on the physical side is definitely not standard. It looks very easy. I was in Cisco, I sold this. It's very easy to sell because it looks simple. Basically, I'm going to tell you, oh, my two boxes look like one, and you just create a port channel to my two boxes. That's all. But the devil is in the details, and this is relatively difficult to maintain. There is a learning curve to implement this. It looks simple, but fact is that you have a lot of corner cases. So if you're already familiar with that, if you already have that, I would say go for it. Otherwise, maybe on the previous model is a good compromise between efficiency and ease of use. So that's why I would not give you a very strict recommendation here. So with that, I'm going to hand over to Shahzad, who is going to show you the operation part. Thank you.
All right. My name is Shahzad Ali, and I am the NSX Solutions Architect. My role and responsibility is to make sure that customers are deploying NSX and designing NSX successfully. In this part of the presentation, I'm going to cover NSX monitoring and troubleshooting. Because oftentimes when I'm talking to customers, they ask me, if I deploy NSX or virtual network, am I going to lose visibility inside my network or inside my virtual machine? And my answer is very plain, simple, and straightforward. And that's not true, because NSX is a standard-based solution, IP-based solution. You can easily integrate NSX into your existing processes and the servers that you have. For example, NSX, all NSX components, they do support syslog. So if you already have a syslog server, or if you have log inside, for example, you can easily push the log to the syslog server, and then you have the visibility, right? So that is one point I wanted to emphasize on. And there is a reason for that, because being part of vSphere stack gives us some advantages. First of all, NSX is part of vSphere, and we are sitting close to the virtual machine. So being close to the virtual machine, when the packet leaves the virtual machine and before even it hits the VNIC, we can see things at the kernel level, right? So this is providing us greater visibility inside the packet that your hardware vendor cannot even provide, right? And the second advantage is that, this is all in software, right? So being in software, as a software solution, the advantages that you get with the software comes with the NSX product. For example, with vSphere you have vMotion, HA capabilities, or a snapshot. You can easily take a snapshot of a virtual machine, or you can export the entire configuration of NSX and ship it to us. For example, we can recreate your issue in our lab and we can solve your problem. So these are the reasons that NSX can easily be operated and managed into your network. And the last point I want to make here is that, with NSX and with vSphere, we are giving you single entry point into your software-defined data center. So you can not only manage and operate your virtual compute, your storage, but now you can also manage and operate your virtual network. So there are many vDS features that I can highlight here, but I will keep my focus on these three tools that are very specific to vDS and NSX. Number one is VXLAN ping, trace flow, and host level packet capture. So let's take a look at VXLAN ping. So VXLAN ping is a tool that we use that can test the connectivity between your VTAPs or VXLAN tunnel endpoints. Why is it important? Let's say you get a call from your customer or your client, and he says that my application on VM1 cannot talk to application on VM2. The first thing that you will do, you will log into the guest virtual machine, VM1, and then you will initiate a regular ping between VM1 and VM2. If the ping is failing at that level, the next thing that you should do is to make sure that your VXLAN connectivity is there. And for that reason, you're going to use VXLAN ping. So in order to demonstrate how does it work in the background in our software, I have set up this network for you. So in the bottom, I have top of the rack switches shown in gray, and then these top of Tor switches are running 3 different subnets for VTAP connectivity. So I have host A, B, part of subnet X, CD, part of subnet Y, and EF, part of subnet Z, as you can see here. So in any network, in any Ethernet-based network, you have 2 types of traffic. One is the unicast, second is the BUM traffic, broadcast, non-unicast, and multicast. So if it is a unicast scenario, it is very easy. VM1 trying to send a packet to VM2, host A knows about the location of VM2 because NSX controller knows about it, and it's going to send it over to VM2 using the same logical switch A. But the broadcast is handled differently in NSX platform. It happens in 2 stages. So in stage 1, host A will send a local copy to all the hosts in subnet X, and it will also send a copy to a remote subnet, for example, subnet Y and subnet Z. Now it is the responsibility of that particular host to replicate it to its local subnet, all the hosts in the local subnet. So that is the reason we call it a 2-stage process. So that is how it works in the background in case of VXLAN ping. And that is the reason we provide you 2 different options in the NSX GUI. One is the unicast and second is the broadcast VXLAN ping. So let me show you a demo of how it works from the workflow or from the GUI point of view. So what I have configured here in the lab, basically I have 2 hosts, host A with .196 and host B with .199. I'm going to ping from host B to host A using logical switch, red logical switch. As you can see, this red logical switch is not extended all the way to host A, so my ping will fail in that situation. In the second part of the demo, I will be using the same source and destination host, but this time using green logical switch. And this time the ping will succeed. So pay attention here, it's going to go quick. So I'm going to click logical switch here, and I'm going to use subnet 20, red logical switch. I have selected and the destination. And I will start my test here, and it fails because it's a red logical switch. Now let's take a look at what happens with the green logical switch. So green logical switch is extended to both hosts, and this time the ping should be successful. Right, so I did the test here, and you can see the ping is successful. This is a scenario if you have an NSX cluster already prepared and you added a new host in the cluster, and for some reason your logical switch is not extended all the way to the other host. In that type of situation, you should use this tool. That is what we recommend. The second tool, which is more powerful than this tool, is called the trace flow tool. This is what we introduced with NSX 6.2 very recently. So this tool allows you to see how your packet is traveled inside our software stack, inside NSX software stack. This is very similar to a situation where you ship a package from source to destination using FedEx or DHL. So FedEx or DHL has a tracking enabled. It will tell you exactly what happened to your packet at every stage. This is a very similar scenario here. So as an admin, you will log into vCenter, and then you will say, I want to trace a packet flow between host A and host B. Your NSX manager will receive the information and will feed it into the NSX controller. And remember, this is a special trace flow packet. An NSX controller responsible for host A, in this case, will send it to the relevant hypervisor, telling the hypervisor that, Mr. Hypervisor, this is a special packet. You need to inject it into the network on this VM's behalf. So this is a special packet, as you can see in number 3. This goes to the destination, and while it is traveling inside the software stack, it's reporting back all the observation back to the controller. So the controller is receiving the information and it feeds it into NSX manager, and you see it in a nice GUI fashion. So I'm going to show you a small demo again. So this time I have 2 short demos. In demo number 1, I'm going to use the green logical switch, and those 2 virtual machines, VM1 and VM2, they are part of the same logical switch. So you will see that there will not be any distributed router involved in that packet flow. In the second flow, it's a ping between or traffic flow between 2 different virtual machines, and you're going to see there will be a distributed router in between. Okay, so demo number 1 without any DLR. I go there, the GUI, click on the trace flow, and now I'm going to select my source virtual machine and that particular NIC on source virtual machine, because you could have multiple NICs on a VM. Okay. Now I'm selecting the destination, VM2 on the same logical switch. and trace. So you can see here in this diagram that it is telling exactly what happened to that packet. So it left the VNIC in sequence number 0. In sequence number 1, it is hitting a firewall. And this is the power of NSX, that your firewall is attached next to the virtual machine. This is where the microsegmentation benefit comes into the picture. Goes into the firewall module inside the kernel, checks the rule, and then leave the firewall, and then go to the source vTap and then to the destination vTap. And then it hits the firewall again, right? So you see the firewall, it is attached next to the virtual machine. So that was without the DLR in between. Same logical switch, simple. In the next demo, source is the same, the destination VM is VM3, and this VM3 is on a different logical switch. So now this trace flow should go through a DLR. Okay, so this is what you see here, distributed logical router, and you can see the power of this tool, how it operates in the GUI and how it shows you the output. And this is what we recommend for you to use. The third tool is basically goes really deep down inside the packet inspection. It's like the crime scene investigation or forensic report, creating a forensic report of what happened to the packet. So there are two important points I want to mention. Number one, with this tool, this is a CLI based tool, you can use capture points. So you can say, where do you want to capture the packet? Is it at the VNIC level? Is it at the uplink level or at the vDS level? So you specify the capture point first. And the second thing that you do, you basically specify the filters, right? So the filter will decide, okay, you want to capture HTTP traffic or VXLAN traffic, for example, in this case. So once you configure that, enter the command, the CLI command, and you can see the output right on the CLI itself. The nice thing about this tool is that you can export the output in a PCAP file. So you can feed it into the Wireshark analyzer, for example, and you can see it in a nice GUI format. We have a session NET5488 that goes more in depth about this tool. It's on Thursday. Okay, so now these are the miscellaneous best practices that we always recommend to our customer. Number one is security, right? So once you have deployed NSX, NSX comes with great security options. Although you have the security ACL and PVLAN option in vDS, but we recommend you to use the security distributed firewall that comes with NSX. Quality of service, really important. If your guest virtual machine needs quality of service, we recommend you to mark them with the DSCP value. That DSCP value is copied to the outer VXLAN header, and then once that packet goes to the physical network, you should have your physical network configured for the right priority, and then it will get the right priority based on what you configured. MTU requirement. MTU is basically not a requirement. It is a must that you should have at least 1600 bytes configured on your physical network. And this is because VXLAN is adding 50 byte of encapsulation there. NIC card selection is very important. This is where the performance comes into the picture, and I have seen it with many of customers where they did not use a proper VNIC and their performance suffered. So we recommend that you use a VNIC that can offload your VXLAN in hardware. Okay, so we are going towards the conclusion. See, these are the key takeaways that I want to highlight. Number one, vDS is the key component of NSX platform, and it is the only virtual switch that is supported with NSX. Number two, VXLAN and vDS technologies, they are decoupling your physical network with the virtual network. So that is important. You can easily create network as long as you have basic IP connectivity. You can do wonders in software. And the last point I want to mention is that vDS is deployed in a large scale deployments. I have deployed it for one of my customers, Columbia Sports, recently, and it is out there and it's being used successfully. All right. So these are the ecosystem partners we have. This is a slide that's just a reference. You should keep it with you. Basically, what we are telling you here that we work with any vendor. These are the resources that we have provided to educate you. My best favorite is HOL, Hands-On Lab. I highly recommend you go ahead and take the HOL labs for NSX. And that is the end of the presentation. Thanks for joining. I hope you enjoy the rest of the show.